Alrighty then, here we go with Chapter 9. And as always, we start with all the concepts that we will cover in Chapter 9. That's what this list is. These are the concepts that you'll be responsible to learn by the time we complete this chapter. Chapter 9 is all about acids, bases, and buffers. We will describe the central role that water plays in acid-base chemistry. Here you can see on this gravestone that over time acid rain has etched away the stone to the point where you cannot even read it any longer. We'll be learning all about acids and acid rain in Chapter 9. Let's start learning Chapter 9 material right now. In this chapter we will differentiate between strong acids and weak acids. The definition of a strong acid is that it completely dissociates when added to water. We can see here that when HCl is added to water, the hydrogen H completely dissociates from the chlorine Cl-. Therefore, HCl, hydrochloric acid, is considered a strong acid. Remember back in Chapter 3 when we learned about the hydronium and hydroxide ions? Well, here we can see that when two waters come together, a hydrogen atom is transferred from one water molecule to the other. This results in the creation of H3O+ and OH-. Since we're talking about acids, bases, and buffers, we of course need to talk about the pH scale and how it's used as a measure of acidity. Here you can see a chart in which the pH runs from 0 at the top to 14 at the bottom, and some common solutions at each of the associated pHs. We defined what a strong acid is a few slides ago. Here we define the properties of a weak acid. Remember that a strong acid completely dissociates, but a weak acid does not. It only partially dissociates. In fact, a weak acid is defined in terms of chemical equilibrium, the same equilibrium that we learned about in Chapter 8. We will also use the Bronsted-Lowry definition of acids to describe the properties of the salts of weak acids and bases, and also how we go on to make buffers using these different salts of the weak acids and bases. Finally, you will learn how to determine the concentration of an acid using a technique referred to as titration. Let's take a look at some properties of acids and bases. When dissolved in water, acids will produce hydronium ions, which many times are simply represented as hydrogen or H+. Acids neutralize bases to produce water and salts, like sodium chloride. Acids turn blue litmus paper red. When bases are dissolved in water, they produce hydroxide ions, OH-. Bases neutralize acids to produce water and salts and turn red litmus paper blue. As we learned in previous chapters, water molecules are very polar and form hydrogen bonds with each other. The hydrogen bond is actually longer than your typical covalent bond. It is 1.8 angstroms in length, whereas the OH covalent bond is only 1 angstrom in length. In solution, water molecules are quite dynamic, moving around, vibrating, rotating, and generally crashing into one another. As this occurs, the bond lengths fluctuate. At any particular moment, a hydrogen atom on one water molecule may be closer to a neighboring water molecule. When this occurs, that hydrogen ion H+ gets transferred from one water molecule to another, resulting in the creation of the hydronium ion H3O+, and concomitantly the creation of the hydroxide ion OH-. The hydronium ion is often referred to as H+ rather than H3O+, but this is only an abbreviation. Bare protons, H+, do not actually occur in solution. The reaction in which a hydrogen is transferred from one water molecule to another is actually an equilibrium process, and thus is represented by an equilibrium constant. We call the equilibrium constant the ion product of water, K sub W. If you remember from Chapter 8, any component that is listed as a liquid is not included in the equilibrium expression. Therefore, the equilibrium constant for water, K sub W, is equal to the hydronium ion concentration multiplied by the hydroxide ion concentration, which is equal to the numeric value 1 times 10 to the minus 14, and that's at 25 degrees Celsius. When the pH is neutral, we have a pH of 7. The hydronium ion and the hydroxide ion concentrations are equal, and the numeric value for each of these is 1 times 10 to the minus 7th molar, and that's for both of the compounds, H3O plus and OH minus. Here's a clicker question that is really testing your knowledge of Chapter 8. Please pause the presentation for about 20 seconds so that the students can answer the question. And we know that the answer is temperature, which is why one must state the temperature when one gives the numeric value for the equilibrium constant. When we look at the equilibrium expression for water dissociation, K sub W, we see right away that there's an inverse relationship between the two concentrations. This is represented graphically in this chart. We can see that as the H plus concentration goes down, the OH concentration must go up. Because of this inverse relationship, if you raise the hydronium ion concentration by adding acid to water, it will force the hydroxide ion concentration to go down. Conversely, if one raises the hydroxide ion concentration by adding base to water, then the hydronium ion concentration must go down. But no matter what, when one multiplies the two concentrations together, the resulting answer must be 1 times 10 to the minus 14th. When the two concentrations are equal, the solution is considered neutral pH. When the H3O plus concentration is greater than the OH minus concentration, it is considered an acidic solution. Conversely, when the OH minus concentration is greater than the H3O plus concentration, the solution is considered to be a basic solution. Here's a clicker question that you really need to think about before you actually punch in an answer. Really read this and read it carefully. Please pause the presentation for about 20 seconds. It doesn't matter what the concentration of OH minus and H3O plus are. The only thing that matters is that the equilibrium constant, the dissociation constant for water, K sub W, is always 1 times 10 to the minus 14th when we're at 25 degrees Celsius. An aqueous solution of gaseous hydrogen chloride molecules is called hydrochloric acid. When HCl is added to water, there will be no intact HCl afterwards. Each HCl molecule reacts with water to form hydronium ion and a chloride ion. This process is called dissociation. As stated previously, every single HCl molecule will dissociate, and that's because HCl is considered a strong acid. When the base potassium hydroxide, KOH, is added to water, no potassium hydroxide molecules will remain. They completely dissociate. So the KOH completely dissociates into hydrated K plus and OH minus ions. Bases that completely dissociate are called strong bases. Here we have a table taken directly from your textbook that lists the strong acids and the strong bases that you are responsible for knowing. If we end up talking about a different acid or a base that's not in this table, it would be considered a weak acid or a weak base. As stated previously, strong acids and strong bases completely dissociate when added to water. Conversely, acids and bases that do not completely dissociate in water are called weak acids and bases. The terms strong and weak do not refer to the concentrations of the acids and the bases, only to the degree to which they completely dissociate into ions in water. Please pause the presentation for approximately 20 seconds. We know from previous instruction that strong acids completely dissociate when added to water, and when they do, they form an exactly equal concentration of H3O plus. Okay, we know that strong acids and bases completely dissociate in water, and therefore the concentration of hydronium and hydroxide can be calculated directly from the concentration of the acid or the base. So let's calculate the concentration of H3O plus upon addition of HCl to water. So what is the concentration of hydronium ion for a 0.01 molar aqueous solution of HCl? We know that HCl is a strong acid, so it will completely dissociate in water, and therefore if the concentration of HCl is 0.01 molar, then the concentration of H3O plus must also be 0.1 molar. We could do the same with a strong base, but in this example there's a bit of a wrinkle, and it's an important wrinkle that you must learn in order to get answers correct on quizzes and exams. For this example, we have a 0.02 molar concentration of calcium hydroxide. We know that calcium is a group 2 metal, and therefore it has a 2+ charge, and will bind 2 hydroxide ions, because they each have a 1- charge. Since there are 2 hydroxide ions for every calcium hydroxide compound, then we have to multiply the calcium hydroxide concentration by 2, resulting in an OH- concentration of 0.04 molar. Okay, now let's get into some slightly more complicated calculations. Here we will use the ion product of water, 1 × 10⁻⁴, to calculate hydronium ion concentration from a given hydroxide ion concentration, and vice versa. So in this case, we're going to calculate the hydronium ion concentration for a 0.001 molar sodium hydroxide solution. We know that sodium hydroxide is a strong base, and therefore a 0.001 molar solution of sodium hydroxide will give us a 0.001 molar solution of hydroxide ion. We set the mathematical representation of the ion product of water, that is H3O plus concentration multiplied by the OH- concentration, that is equal to 1 × 10⁻⁴. We use basic algebra to solve for the unknown, the H3O plus concentration, which we calculate to be 1 × 10⁻11 molar. The molar concentration of hydronium ion typically ranges from 1 molar to 1 × 10⁻⁴ molar. To simplify the pH scale, this range of concentrations is compressed using a logarithmic scale that we call the pH scale. To calculate the pH from the concentration of hydronium ion, one first takes the log of the H3O plus concentration and then makes that negative by multiplying it by -1. You should try this on your calculator. Enter in 1 × 10⁻⁷ and then hit the log button. Your calculator should now read -7, and multiplying that by -1 gives the pH of 7. Conversely, if given the pH, one can calculate the H3O plus concentration by raising 10 to the negative power of the pH. So on your calculator you should punch in the number 10, then hit the Y to the X button, enter in -7, and the answer should be 1 × 10⁻⁷. You can also do this by using the inverse log button on your calculator. The pH of a solution is invariably measured using a pH meter. You should familiarize yourself with the scale shown here, which relates the H3O plus concentration, the values underneath the orange and blue arrows, to the pH values which are on top of the arrows. The central point at the middle of the 2 arrows represents neutral pH, pH 7, where the concentration of H3O plus is 1 × 10⁻⁷. As we move to the left on the scale, the H3O plus concentration increases, while the negative log of that concentration, the pH, actually decreases. The converse is true to the right of the scale. As we move to the right, the H3O plus concentration decreases, while the values for the pH increase. It is important to recognize a different way of calculating significant figures when dealing with pH values. The number to the left of the decimal point corresponds to how many times the number 10 is multiplied by itself to arrive at that number. Therefore, it is considered a placeholder. Because of this, any time a logarithm is taken on any number, only the digits to the right of the decimal point are significant. So a pH value of 7.45 only has 2 significant figures, and a value of 12.3 only has 1 significant figure. At the top of this figure, we have a chart that is similar to the one seen in the previous slide. But in this case, different solutions are listed based on their pH values. Everything to the left of pH 7 corresponds to solutions that are acidic, they have higher concentrations of H3O+, and they have correspondingly lower pH values. So it goes from 7 down to 1. The solutions to the right have lower H3O+ concentrations. These are considered basic, and therefore they have higher corresponding pH values. Please pause the presentation for 20 seconds. And by now we should know that acids release hydronium ions, which are sometimes denoted simply as H+. For this question, you'll have to determine which one of these four is a weak acid. Please pause the presentation for about 25 seconds. And the answer is D. The weak acid is H2SO3. The other three compounds, hydrochloric acid, sulfuric acid, and nitric acid, are all strong acids, and you'll have to memorize that and know that for your next exam. For this question, you're asked to differentiate between strong bases and weak bases, and therefore you will likely have to refer back to the table of strong acids and bases in order to be able to answer this question. Please pause the presentation for approximately 30 seconds. And the answer is D, aluminum hydroxide, which is a weak base, and therefore the other compounds shown above it are all considered to be strong bases. Logarithmic scales are based on powers of tens. Let's take a look at this table. On the left we have the familiar decimal notation, running from a value of 1 down to 1 billionth by factors of 10. The middle column represents scientific notation, and the third column is the negative log of the different concentrations, which of course is the pH. So we can see that when we change the pH by 1 unit, say when we go from a pH of 4 to a pH of 3, we have actually increased the H3O+ concentration by a factor of 10, or 10 times. Conversely, if we increase the pH from 4 to 7, we decrease the hydronium ion concentration by a factor of 1,000, 3 orders of magnitude. This is a concept that you should study and understand well, because it invariably ends up as a question on exam number 3, or quite possibly on the final. Let's review what we've learned thus far about acids and bases. A neutral solution has a pH of 7. The hydronium ion and hydroxide ion concentrations are equal, and the numeric value is 1 times 10 to the minus 7th molar for both of the compounds. In acidic solutions, the pH is less than 7, and the hydronium ion concentration is greater than the hydroxide concentration. In basic solutions, the pH is above 7, goes from 7 to 14, and hydroxide ion concentration is greater than the hydronium ion concentration. These are facts that you have to dedicate to your memory.